All right, this is the most complicated type of calorimetry question that you could come across. This is one where you're given all the information except for the final temperature. And in this type of question, what you have to do is you have to set up two equations and solve for the final temperature. And let's see how to do that. So ultimately, what we're going to do is we use the fact that all the heat from the metal goes into the water. Okay, and all that changes is the sign here. So the exact same amount of heat that was in the metal ends up in the water. But since the metal is cooling down and the water is heating up, we need a negative sign here. Well, what that gives us is, so the mass of the copper times the specific heat of the copper times the final temperature minus the initial temperature of the copper is equal to a minus sign times the mass of the water times the specific heat of the water times the final temperature minus the initial temperature of the water. Okay, the final temperature is going to be the same. The two objects are in contact until they're at what's called thermal equilibrium, and so the metal will cool down and the water will heat up until they're at the same temperature. So now we need to go into our problem and find all the pieces. So the mass of the copper, specific heat of the copper, final temperature is what we're looking for, the initial temperature of the copper, all right, let's go ahead and do that for our metal. So the mass is 155.4. It initially was at 425 degrees C. The final temperatures are unknown. The specific heat for the copper is 0.385. Now we're going to do the same for our water. The mass of the water, specific heat of the water, final temperature, which is again going to be an unknown, and the initial temperature of the water. So the mass of the water is 500 grams. Its specific heat is 4.184. The final temperatures are unknown, and the initial temperature is 22 degrees C. All right, now we'll just put all these pieces in. So 155.4 times 0.385 x, our final temperature, minus 425 is equal to, and I cannot lose this negative sign that comes from here, this negative sign times the mass of the water times the specific heat of the water, x minus 22. All right, now I'm going to multiply 155.4 times 0.385 times x. 155.4 times 0.385 times x gives me 59.8. I'll just keep one decimal point, 59.8x. And now 155.4 times 0.385 times my minus 425 gives me a minus 25427. Okay, now the other side of the equation, I'm going to do my minus here, minus 1 times 500 times 4.184 times x gives me a minus 2092x. And now minus 500 times 4.184 times minus 22. Okay, and this gives me a positive value, plus 46024. All right, what we're going to do now is move everything with an x to one side of the equation and everything without an x to the other side of the equation. 59.8x plus 2092x is equal to 46024 plus 25427. 95.8 plus 2092 gives me on the left side here 2151.8 x is equal to 46042 plus 25427, 71451. Okay, now simple division will do what we need to do. Okay, so 71451 divided by 2151.8. Okay, this gives me 33, and the units here are degrees C. What's pretty interesting that's happened here is we had a piece of metal, and the copper went from 425 all the way down to 33 degrees C. But our water went from 22 just up to 33 degrees C. And so it took all of this heat coming out of this copper to bring the metal up just 11 degrees. Right, we went almost 400 degrees here to bring the water up by 11 degrees. There's a couple reasons for that. So there's more water. So there's 155 grams of copper. So there's roughly 3 times the amount of water here. But also, the other thing that makes a huge difference is this heat capacity. So the heat capacity is about 10 times higher, over 10 times higher for the water versus the copper. And so those two things together shows why we have to take so much, have such a large temperature change for the copper to bring just a small temperature change about for the water.